Yes.
Okay, great. All right, folks. Once again, very good morning, good afternoon, good evening. Once again, depending on whichever part of the world you're logging in from today, it's a matter of great privilege and sheer delight to welcome our distinguished speaker, Professor Dame Jocelyn Bell Burnell. Oh, sorry. I think. Oh, I'm sorry. Oh, apologies for that. That was the YouTube tab which is on my laptop. I just closed it. So it was echoing what I just said. So back to what I was saying, I'm sorry for that. So we have Professor Burnell. I'm sure she doesn't need an introduction, but just for sake of completeness, let me say the following. Professor Burnell is an astrophysicist and is currently a visiting professor of astrophysics at the University of Oxford and a fellow of Mansfield College. As a grad student, we all know she discovered the first radio pulsar way back in '67. And in fact, the chart of her recognized evidence of a pulsating radio source, or pulsar in short, is preserved as an exhibit at the Cambridge University Library. She has an incredibly long list of awards and honors. I would mention a few. So she is the co-recipient of the Albert A. Michelson Medal of the Franklin Institute of Philadelphia in '73, the Robert Oppenheimer Memorial Prize from the Center of Theoretical Studies, the University of Miami in '78, the Beatrice M. Tinsley Prize of the American Astronomical Society in '86, the Herschel Medal of the Royal Astronomical Society in '89, the Magellanic Premium of the American Philosophical Society in 2000. She was elected a Fellow of the Royal Society in 2003, March 2003, a Fellow of the Royal Society of Edinburgh in 2004. She got the Grote Reber Medal at the General Assembly of the International Radio Science Union in Istanbul in 2011. She's a recipient of the Royal Medal of the Royal Society in 2015. She was declared she was the recipient of the Women of the Year Prudential Lifetime Achievement Award in 2015, and the Institute of Physics President's Medal in 2017, the Grand Medal of the French Academy of Sciences in 2018. And this is the real interesting part. She is the recipient of the Special Breakthrough Prize in Fundamental Physics in 2018. And she donated the entire £2.3 million to fund women, underrepresented ethnic minority, and refugee students to become physics researchers. And the funds are to be administered by the Institute of Physics. She is a recipient of the Gold Medal of the Royal Astronomical Society in 2021. In 1999, she was appointed the Commander of the Order of the British Empire for services to astronomy and promoted to Dame Commander of the Order of the British Empire in 2007. In Feb 2013, she was assessed as one of the 100 most powerful women in the UK by Women's Hour on BBC Radio 4. In Feb 2014, she was elected president of the Royal Society of Edinburgh. In fact, she's the first woman to hold that office. In 2016, the Institute of Physics renamed their award for early career female physicists as the Jocelyn Bell Burnell Medal and Prize. In 2016, she was elected an international member of the American Philosophical Society. In 2020, she was elected a Legacy Fellow of the American Astronomical Society. So with that, I very humbly request Professor Burnell to please deliver her lecture. Professor Burnell, please.
Thank you very much, Ashok. Just get these screen sharing up. Come on. Thank you. So thank you for that very generous introduction. And good evening, good afternoon, good morning, depending on where you are. It's early afternoon here in Britain. And I want to talk today about the discovery of pulsars and what pulsars have taught us about physics, basically, since their discovery. So I'll talk a little bit about the discovery of pulsars, a little bit about black holes, some tests of fundamental physics that we can do using pulsars, and gravitational radiation. So I'm covering a lot of ground. It's more a case of pointing out to you things that you might be interested in rather than going into them in great detail. So the discovery of pulsars comes from radio astronomy. Radio astronomy started after the Second World War in the late 1940s, using radar receiving equipment that was now surplus to needs and has gradually built up since then. This particular slide shows the big radio telescope at Jodrell Bank, which was one of the early big telescopes, with a lovely image of the setting sun as well. This telescope's now been made a World Heritage Site, so perhaps one of the first to be so labeled. So radio astronomy, when it started, they didn't know if they were going to find much or not. And in fact, sorry, my screen keeps jumping on. In fact, they found a lot of stuff that they couldn't have known was there, including some particularly strong emitting objects that became known as quasi-stellar radio sources, or quasars. Quasi-stellar because when the optical astronomers looked at the positions that the strong radio signals were coming from, they found some sort of star-like objects. But star-like objects with a large redshift, which implied far out in the expanding universe. So it was quite surprising that such strong sources could also be so very far out in the universe. And they became known as quasi-stellar radio sources, or quasars, thereafter. Now, at the time that I started as a graduate student in radio astronomy, there were about 20 quasars known. The number really, a bigger number was really needed. It was rather too small a sample, and my particular project was using a radio telescope to find more quasars. It undoubtedly was successful. I got the number of quasars up from 20 to about 200. A little bit of biographical background. I started life in Northern Ireland. I had some of my schooling in the north of England at number 2. I did my bachelor's degree in the University of Glasgow at number 3. And then I go south to Cambridge at number 4. There's some indication on this map of where the high ground is. The mountainous areas in Britain are in the north and west. The much flatter land and the more affluent part of the country is to the south and east. And so for the first time in my life, I have ventured into this affluent southeast of England. I don't know what it's like in India, but I think there is an unofficial gradient in the country in Britain, certainly as perceived by people in the south and east. They consider themselves to be the ultimate civilization, and people from further north and west are uncouth savages. So I was an uncouth savage turning up in this very civilized place. I quickly recognized that I was an outsider, in part because there were very few women, but also because I was from the north and the west. And I was overawed. People seemed to be very clever and quite keen to let you know they were very clever. And I felt I wasn't that clever. I felt they'd made a mistake admitting me to Cambridge. I thought they would discover their mistake in due course and they'd throw me out. We now have a name for this. It's called imposter syndrome. I don't know if it's a term you're familiar with, but it's quite an issue in Britain, particularly if you work somewhere prestigious like Oxford or Cambridge. In bad cases, the student will say, they've made a mistake admitting me, they're going to throw me out. I'd better leave before they throw me out. And within a week of the new academic year starting, they've gone, they've disappeared back home. Well, I'd had a battle to get there, so I wasn't going to walk out of my own accord, but I did know for sure that they'd made a mistake, that they would discover their mistake and they'd throw me out. And my policy, which I recommend to any of you if you ever feel like this, my policy was to work as hard as I could so that when they threw me out, I would not have a guilty conscience. I'd know I'd done my best, and it just wasn't good enough for Cambridge. I spent 2 years building a radio telescope with several other people. And then when it was built, they disappeared to other projects and I was left to operate the telescope. At that time, this is the late 1960s, the University of Cambridge had one computer. It had memory comparable to the memory of your laptop. It was a lot bigger. It occupied a whole room because we didn't have transistors, or very rarely had transistors. So it was operated with vacuum tubes or valves. And very few people had time on it. And my boss did not. So our data came out on this paper chart, as you see in the diagram. And I spent most of the year analyzing these chart recordings. The telescope produced 30 meters of chart every day. So after operating the telescope for 6 months, I had over 5 kilometers of data. It was a huge job. Now, it was a very good telescope for finding more quasars. I found about 180. I got the number of known quasars up from 20 to about 200, which is a good size sample. But in amongst the quasars and in amongst the inevitable radio interference, there was just occasionally a signal that I couldn't make sense of. And in the little diagram here, you see the first sighting of it. The labeling, needless to say, was done a lot later, but this was the first detection. It's the signal, the left hand of the two signals. The right hand one is man-made interference. For the benefit of the students, if you study these two signals, the one labeled CP1919 and the one labeled interference, you'll see they look different. And I knew they looked different, which is why I knew it wasn't interference. It didn't look like a quasar either for different reasons, so that's why it puzzled me. But let's just spend a moment examining how and why they look different. In the signal labeled interference, the spikes go up and down. In the signal labeled CP, the first pulsar, they go mainly up. In the interference signal, you can see chart paper between the spikes, whereas in the pulsar signal, at least at the left-hand edge, they're jammed so tightly together, you can't see any chart between them. When you make that kind of comparison, you are doing what's called Fourier analysis. You're talking about the amplitudes that are present. The interference ones are positive and negative. The pulsar ones are largely positive. And you're talking about the frequencies. In the interference case, the frequencies are lower. You can see chart paper between the spikes. Whereas with the pulsar signal, they're higher. So that kind of comparison is Fourier analysis. Fourier analysis unpacked for the student who's scared of Fourier analysis. So it was a very small part of the chart paper, but because I was being very thorough and because it was puzzling, I registered it at a subliminal level. And then after I'd seen it a few times, I realized I'd seen something like this before and was able to pull out previous recordings from that bit of the sky and see that, yes, on occasion, I had seen it before. wasn't always there, and it's usually fairly weak, to be honest. My supervisor rightly observed, I'll go back a slide. My supervisor rightly observed that because this signal is so close packed, you can't really see what's going on. We need an enlargement. And the way you get an enlargement with rolls of chart paper and chart recorders is you run the paper faster underneath the pen and it all gets spread out. You couldn't do that permanently. It would get through too much paper too quickly. So what had to happen was that I, the grad student, went out to the observatory shortly before, I lost my pointer, yeah, okay. Beg your pardon. Shortly before this signal was due to transit, do a high-speed recording and then switch back. And finally, I got it, and this upper trace is what came in. The label was added later, I have to say. Oh dear, sorry, my computer has a mind of its own. The bottom trace is time pips, 1 second time marks, which were very conveniently broadcast in Britain. And the upper signal is the enlarged trace of that funny signal. You'll see that the pulses are about 1 1/3 seconds apart. Let me go back and find my pointer. So the spacing here is about 1 1/3 seconds. And even when they disappear for a bit, they come back on beat, in phase. Well, something that does something on a time scale of 1 1/3 seconds is quite small. And indeed, the pulses have quite sharp rises and falls, which means it's even smaller than that. So it's something very small, which was a bit of a puzzle. It wasn't local radio interference. It wasn't a fault with my equipment. My supervisor was quite sure I'd wired the telescope up wrong somehow, but it wasn't. But it was a bit of a puzzle because the pulses are short, which means it's small, but they kept the pulse period very accurately. I kept recording this day after day after day. And the pulse period, we got it to 6 or 9 decimal places, and it was very, very steady, except for the Doppler shift due to the motion of the Earth around the sun. Now, if something's going to maintain its pulse period, it's got big reserves of energy, so it's big and it's small. Nyaha. Not obvious what's going on. A colleague managed to get a dispersion measurement. He took 2 of my receivers, tuned one up in frequency slightly, tuned one down in frequency slightly, and found that the pulses came first in the higher frequency receiver. And measuring the delay between the two and making a guess at the electron density in space, because it's electron density that causes dispersion, we managed to get an estimated distance of 200 light years. So it's way beyond the Earth, way beyond the sun and the planets, but in our own galaxy. Tony was quite concerned that it might be little green men signaling. If they were little green men, they'd be likely on a planet which orbited their sun, and we would see Doppler shift on the pulses as they orbited their sun. So I kept on making these recordings. As I've said, we found a Doppler shift due to the motion of the Earth around the sun, because Doppler shift works for the observer as well as for the source, but no sign of those little green men or whatever moving. And then I found a second, and rather rapidly after that, a third and a fourth. And that scotched the little green men idea. There aren't 4 lots of little green men in different parts of the universe, all deciding to signal to planet Earth using the same frequency and the same mode of signaling. That's just not on. This has to be some new kind of star. And we now know of about 3,000 of these objects, although that particular telescope that I was using, I think, only ever discovered one more. So it's some kind of star. It turns out that they're a very compact kind of star, which we call a neutron star, or sometimes they're labeled pulsars for pulsating radio stars. The existence of pulsars, which are clearly very small, less than 10 kilometers radius, and very dense, because they're made of stuff like the sun, made of a mass like the sun. Something small and dense like a pulsar, or as we now know, a neutron star, made black holes seem much more likely, much more plausible. And indeed, just a few years later, X-ray astronomers studying the X-ray source Cygnus X1 were forced to conclude that the compact object in that binary star system was a black hole. So black holes fairly quickly followed after pulsars. If we hadn't had pulsars, I think the recognition of black holes would have been delayed because they would have been such a large leap from conventional stars. See if I can get this. Yep. This is a lovely video, which you can find on the web. It's looking in the infrared at stars around the center of our galaxy. The center of the galaxy is where this star shape is, although we can't see anything at the shape of the star. Now, I guess everybody will have learnt Kepler's laws, like a body moves at a steady velocity in a straight line, unless affected by some other acceleration or force. There is not a straight line to be seen in this video. All these stars are making looped. Indeed, this one makes a very nice ellipse with this position at its focus. You'll find some other nice curved tracks as well. So this green one is also curving nicely. There's something with very, very strong gravity there. And it turns out that it's a massive black hole, not a star mass black hole, but millions of that, about 4 million times a solar mass. Excuse me a moment, there's somebody in the house. Excuse me. Okay, post arriving. Right, so pulsars, neutron stars made black holes seem more likely. We've also used pulsars for testing fundamental physics, and I want to introduce you to some of those issues as well. It was reputedly Galileo who went up to the top of the Leaning Tower of Pisa and dropped from the top two objects of different mass or different material. He believed they would drop at the same rate. His colleagues disagreed. He apparently dropped two objects and they did fall at the same rate. The test has been repeated. US astronauts on the moon dropped a hammer and a feather, which is reputedly one of the pairs of objects that Galileo dropped. They dropped a hammer and a feather on the surface of the moon, and you can see they are falling at the same rate. They would not fall at the same rate here on Earth because of air resistance. The feather will waft its way slowly to the ground. The hammer will fall fast. But on the moon, where there's no air, the two drop at the same rate as predicted by Galileo. This test has now been repeated in many ways, and the statement that objects fall at the same rate regardless of mass or composition is good to about 1 part in 10 to the 14. I believe that's the current limit. We have an interesting example of a pulsar twinned with another star and the pair orbiting a third star. This allows us to test another issue, because the pulsar is orbiting a white dwarf, and this is another white dwarf. So the gravitational field of this white dwarf will act on both the pulsar and the white dwarf, and they're made of different materials. And it turns out this is one of the best ways to test Einstein's statement that the nature of the material doesn't matter, it experiences gravity in the same way. Because if the pulsar behaves differently under the gravity of the central star from its companion, then the orbit of this pair of stars around each other will gradually change. So this has been subject of a test that's been going on quite a while. It's a really tough one to do. They're a good pair because the pulsar self-gravity is a good deal stronger than the white dwarf self-gravity. They are struggling to understand experimental uncertainties, basically. And so I don't think there's been any statement yet, but clearly there is not a gross effect, or we would have heard about it by now. Yeah, I think this says the same thing. If the pulsar and its companion fall at different rates, their binary orbit changes. Oh, and the eccentricity of the orbit will point towards, in this case, the star at the center that they're both orbiting. Pulsars have been used to test others of Einstein's theories. The first detected pulsar in a binary system was detected around about 1974 and showed evidence of gravitational radiation. It was a pulsar in a binary system, pulsar twinned with a white dwarf, and they measured it for, well, longer than this now, but certainly 25, 35 years. And the data points are what they found for what's called the cumulative shift. So good string of data points, and it does continue beyond this now. The line is not the best fit. The line is Einstein's prediction, the general relativistic prediction. And clearly it's good. It's very good fit. 2010 figure was that it was consistent with general relativity to within 0.3%. There has subsequently been discovered a double pulsar where two pulsars orbit each other. And that work still continues, but a figure from about 5 or 6 years ago said it was consistent with general relativity to within 0.02%. So general relativity is looking pretty healthy. So well done, Einstein. It's an interesting double pulsar. It's quite fast, a 2.4-hour period. And the plane of the orbit it happens is almost edge on, so we can see eclipses. And I've already given you this figure. I think I've got my slides in the wrong order. I think I have said all of this. You don't want that figure for the third time, I'm sure. So moving on to my final topic, which is gravitational radiation. Some people haven't met this, so I will start way back if you don't mind. Imagine a mattress on a bed. You put a heavy weight on the mattress bows underneath it. If you were to move the weight up and down, the bowing would change as well, the size of the dent. Now, space-time's a bit like the surface of your mattress in that a heavy body will cause a bowl-shaped dent in your mattress. And if you were to move this heavy thing up and down or roundabout or something, you would send out ripples through this surface, which is a representation of space-time. So this is an animation from Wikipedia. It's a visualization of a mathematical calculation. There are a pair of neutron stars here orbiting each other, And as they orbit, they send out these waves in space-time, which are gravitational waves. They're not usually as strong as this. They're not as visible as this, but for the animation, they've been enhanced manyfold. And they travel out at the speed of light. Now, as that pair of objects orbits each other, they're losing energy because of the gravitational radiation they're sending out. And when they lose energy, they move closer. And when they move closer, they go round faster, and the gravitational wave gets stronger. So they lose more energy and move closer and go round faster still and lose yet more energy and move closer and go faster and ultimately merge. And this is the waveform that you expect. It's the theoretical waveform. So it's oscillating fairly steadily, but the amplitude is gradually increasing. The frequency is getting higher. The amplitude is increasing. The frequency is getting higher, and they merge. And this is the kind of pattern you expect from gravitational radiation. Now, gravitational radiation is a quadrupole radiation. I don't know if you can see my picture, but it's a bit small, but you do that, and then that, you do that, and then that, you do that, and then that, and that. If you can't see the picture, put your left hand near your left shoulder and then stretch out your left arm. Put your right hand near your right shoulder, stretch out your right arm while pulling back the left arm. Put out the left while pulling back the right, and so on. This would be much easier face-to-face, folks, wouldn't it? But it turns out that because that's the way a gravitational wave works, an instrument that's very good for detecting it is a Michelson interferometer, or sometimes known as a Michelson-Morley interferometer, which has a light source. The light source split into two parts. One lot goes along that way, one lot goes at right angles to it. Two are combined, and you observe with your eye or with the photodetector. And if a gravitational wave comes along, first of all, that arm will extend and this one shrink, and then vice versa. This one will extend and that one shrink. And you'll see fringes going past here at the detector. It's a very neat technique for doing it. It was first really appreciated by Ron Drever, who was my final year tutor when I was an undergraduate in Glasgow University. And Ron was a very inspiring tutor, although also a pretty useless one, in the sense that we say, Professor Drever, we don't understand what Professor so-and-so is teaching us in solid state physics. Can you help? And he'd say, no, I don't understand it either. Let's talk about, and we'd talk about something like this. So it was very stimulating, also a bit frustrating, but he was very, very clever. And I made a mental note to watch whatever field Drever moved into, and he ended up in gravitational radiation. So a passing gravitational wave causes the pattern of light fringes to shift. If you have a 4-kilometer interferometer, I do mean kilometer, it means the test mass movement is about 10 to the minus 18 of a meter, which is about the size of a quark. Longer arms would give bigger movement, but you lose light intensity with longer arms and they're harder to control. So at the moment, we're working with arms that are several kilometers long. Gravitational wave amplitude is normally quoted as a strain, so change in length over length. And you're typically expecting about 10 to the minus 21 for most reasonable things up in the universe. So it's very, very small. Interestingly, the luminosities emitted by whatever you're observing can be really, really strong, 10 to the 50, 10 to the 52 watts. But space is very stiff And so the gravitational wave amplitude is very, very small. However, they have done it. They have made detections, and they're making detections more and more rapidly. And this spectrum is opening up very fast. There is going to be a gravitational wave detector in India. I'm not quite sure what the state of progress on that is. I think a site has been identified. I don't know if any construction has started, but it's incredibly useful to have gravitational wave detectors. And it'll be a bit like this, all buried underground, of course. They'll be very useful to have a number of these because the signal is so small. You really want it to be seen by several detectors at once for you to believe it. Otherwise, it could be rubbish. And a detector in India will be incredibly important for this. So I hope it gets built soon and successfully. Now, they have actually detected gravitational radiation in September 2015. This is the signal. There were 2 detectors in the USA, Livingston shown in blue and Hanford shown in the pink color. And initially you see there's not much agreement at all, but here they begin to see the same signal, albeit with noise. And the signal's growing and getting faster and faster and faster, and there's a merger. There's a ring down. And that was the first gravitational wave detected. And I don't know why I've got 2016 up there, probably because that was the year of publication. And it turned out to be the merger of 2 massive black holes. We didn't know that black holes in this mass existed. The gravitational wave astronomers have shown us that there are actually rather a lot of them. We expected the first detection to be a merger of 2 neutron stars. There was a merger of 2 neutron stars a few years later in 2017. And they were detected first by their gravitational radiation. And fairly quickly, the gravitational wave astronomers could say, yep, that was 2 neutron stars merging. Unfortunately, because there was a limited number of gravitational wave detectors, the position on the sky was very, very poorly defined. However, people studying gamma rays spotted a very short, sharp burst of gamma rays from near the edge of a galaxy within the error circle of the gravitational waves. And there was a temporary bright optical event as well. That all happened about 2 seconds after the gamma ray after the gravitational wave detection. So we're pretty certain we're looking at the right thing. It's a galaxy about 130 million light years away. Right, I'm going now to talk about formation of the chemical elements or formation of the nuclei of the chemical elements. I've got my slides in the wrong order. Okay, so I'm going to talk particularly about creation of some of the heavy elements in the periodic table. Stars, exploding stars, will create the chemical elements up to about iron. Beyond iron, we have a problem. Iron is the pits. You can take light elements like hydrogen and fuse their nuclei to make the nuclei of heavier elements and heavier elements and heavier elements to iron. And that gives out energy. This is how the sun shines, for instance. You could take uranium and split it, fission it, and get energy out. This is behind a bomb, and some nuclear reactors will do this. And you can do that as far as iron, but you can't do anything with iron. It is literally the pits, and so are the other elements close to it. So stars can start with hydrogen and helium and make chemical elements up to about iron. But how does nature make these chemical elements? because nature obviously has made these chemical elements. And it usually makes elements heavier than iron step by step, adding a particle. So you start off like this and you add a particle, usually a neutron, one at a time, gradually building the bigger elements. And that's fine as long as the bigger element you make is stable. However, there are unstable nuclei, and the question is, how do you get past these? How do you add something to an unstable nuclei to make the next biggest? And I have an analogy. You have to cross a river. There are some convenient stones, and you can step across from stone to stone. But suppose the stone that you're about to step onto is unstable, it wobbles. What happens? Well, you fall in the river, or maybe you step in the river, or you somehow manage to get your balance. But actually, there's something you do almost intuitively as soon as you find this one is unstable. Just pause a moment and think, what do you do almost intuitively if you're stepping across a river and find that the stone you've just stood on is wobbly and risks throwing you in the river? You jump on quickly. It's almost instinctive. You go, woo, whoop, and on to the next one and hope that it is stable. Nature does something similar. When it finds a radioactive element, a radioactive nucleus, as it's stepping up the periodic table, what it does, if it can, is jump quickly onto the one beyond before this wobbly one can disintegrate. So you need to be adding two particles quickly to bypass an unstable nucleus, and you hope that the next one up is stable. So you need lots of particles around so that two can be added in quick succession. We used to think this happened during a supernova explosion. This photograph is of a recent nearby supernova in the Large Magellanic Cloud, 1987A. It's one of the best we've had to observe. However, although we thought this could happen in a supernova, we're no longer clear that the conditions are right there for long enough to create heavier elements like gold and platinum to get past an unstable nucleus. We need a more violent, a hotter explosion. And it turns out that neutron star mergers, although we've only seen one so far, or there's only one published so far, neutron star mergers are now believed to be the site of heavy element formation, as they provide a hotter, more violent explosion than a supernova. So I will pause there, stop there. I've covered a lot of ground rather fast. I hope it has been of interest, and I hope at least some of you have been able to follow some of it. Thank you very much.
Thank you so much, Professor Burnell, for that beautiful talk. And it was especially the earlier part of the talk, the initial part of the talk, where you were telling about your graduate student days. That was, I'm sure, extremely inspiring to so many of us. Thank you once again. So can we please have a round of applause for Professor Burnell's lecture? Okay, Professor Burnell, can you still hear me?
Yes, thank you. I can indeed.
Yes, great. So would it be okay if we take up a few questions which have popped up in the chat
Yes,
session? Excellent.
yes, of course.
Okay, great. So let's do that. And here we go. So, okay, so there is a question by Arnav Das, and the question is, what are some of the current frontiers of research in pulsars?
A lot of the current frontiers are ones that have been with us for quite a while, about how you produce a pulse from a pulsar. It involves understanding the pulsar's magnetosphere, which has huge magnetic and electric fields and high speeds of rotation and strong gravitation. And it's a tricky field because you can't make many simplifications. That's one of the ones perhaps where there's been some progress, but not huge. There's also research on the insides of the neutron stars, the pulsars. What's their structure? What are they made of? Because you will appreciate that is extremely high density stuff. So those are two areas with very difficult physics because of the extremes. I've mentioned the ones about testing Einstein's theories. That's another hot area as well. Yeah, so there are many others, but those I think are perhaps the more sophisticated ones.
All right, great. So there's a query by Pranav Hariharan, and the question is, does the laser interferometer have some blind spots in analyzing some of the gravitational waves? And how can we improve it?
Right. I think the biggest improvement needed is in sensitivity, basically. There'll be blind spots in identifying where the signal has come from, unless you have a fair number of detectors around the world, which is why the Indian one is so important. At the moment, we have 2 detectors in the USA, and a Japanese one has fairly recently started. And there's a small one in Northern Europe, which can be some help, but it is a good deal smaller. We badly need more of the level of sensitivity of the big ones.
Okay. There's a cute little question by Ganesh Subramaniam, and says, is gravitational radiation the same as gravitational wave?
Yes, it is. Sorry. Thank you very much for that. Yes. Yep. Same thing.
Okay. Yep. Great. And all right. So there's a question by Devika PB, and the question is, what causes the pulsar to emit in radio frequencies?
Yeah. Well, the physics answer is electrons. It's usually electrons that produce radio waves, but that's bypassing a lot of very difficult physics. The understanding the emission mechanism of a pulsar is really tough because you've got strong gravity, you've got strong, huge electric fields, huge magnetic fields, rapid rotation. You can't make any simplifications to make the problem more tractable. It's horrible. And we've actually made only limited progress on that, I must admit.
Okay. There is a 2-part query by Alex. The first part is, can you explain a bit more about what is a quadrupole radiation and how is it different from other types? The second is, when the first of these signals of these new unknown objects, the pulsars, were received, and the initial hypothesis of green men sending signals, etc., were discarded, how was the theory of these pulsars developed, and how are the other attributes like the size of the mass, etc., measured?
Good. Thank you. Well, quadrupole radiation, excuse me, is something that we haven't really had to deal with in physics until gravitational waves came along. It's not simple up and down. It's a push, sometimes described as a push-pull. Take 2 dimensions at right angles. One dimension is pushing when the other is pulling, and then the second one is pulling when the first is pushing when the first one's pulling. So it's a funny sort of radiation. It's not simple up and down. That's why it's called quadrupole. Well, not why it's called quadrupole. It is called quadrupole. Sorry, I've forgotten the second part of the question.
Yes. So it basically is asking, you talked about this, the green men hypothesis being discarded and be replaced by pulsars. So the question is, how are the attributes of the same, like the size of the mass measured?
Right. Okay. So we never really believed in the little green men hypothesis. And I found a second, a third, and a fourth, which really means there aren't that many lots of little green men, I'm sure. So the little green men hypothesis disappeared as I found more pulsars. Where to go next?
I mean, how are the size of the masses of these objects measured?
Right. Well, the masses you can measure if you got them in a binary, and we found some in binaries. And by studying the binary orbits and knowing what the partner object is, you can get an estimate of the mass of the object. There was an interesting debate initially about whether it was a white dwarf that was oscillating or a neutron star that was rotating. White dwarfs are the next most compact object. And Tony, my supervisor, was keen on the idea that it was rapid repeated shocks in the atmosphere of a white dwarf. Whereas the alternative theory, which turned out to be correct, was the rotating neutron star. Now, the way you can distinguish between those two is that as a rotating object ages, tires, it gets slower. Whereas with an oscillating object, as it gets tired, its amplitude gets smaller, but it quivers very, very fast and stops. So with a vibrating object, the period will get shorter. With a rotating object, the period will get longer. And once we had particularly the pulsar in the Crab Nebula, we could measure how the period was changing so that the period was getting longer. So it had to be a rotating object. That was a neat bit of science. Beyond that, it's not simple describing how the emission is produced because of all the extremes. Pulsars are extreme in just about every dimension you can imagine. Huge magnetic fields, huge electric fields, huge gravitational fields, rapid rates of rotation, high density, etc., etc. So all the physics is that much more complicated because you can't make any assumptions that we can ignore the electric field. No, you can't. We can ignore the magnetic field. No, you can't. And so on. Thank you.
All right, okay. So there was a question by Rajneesh Kumar, and he asks, what is meant by the stiffness of space-time?
Right. Stiffness of space-time is a measure of how well it transmits. Let me start that sentence again. If you were able to thump space-time, it would, how well is that burr transmitted through space? That's a measure of the stiffness. If space is very, very stiff, then a big thump produces a tiny, tiny burr. If space is more soft and spongy, you can get big waves. It turns out that space does not give big waves. Space only gives tiny amplitude waves. It's stiff.
Okay, great. So there's a question by Anil Gauri Shetty, who, by the way, is one of the co-conveners of the Institute Lecture Series. So he's the guy who gives the nod to us. So we've got to take his question. And the question is, what would be the temperature during neutron star mergers, which are the sites for formation of heavy elements?
Yeah. I don't have a figure for that, I'm afraid. I don't have it with me or in my head.
Okay.
Obviously, pretty big.
Okay, great. Okay, so there is a question by Deepan Betal, and it says, could there be any Doppler shift in gravitational radiation, perhaps due to an accelerating observer?
I guess there could be. The complication is that the frequency of the gravitational wave is changing anyway as the merger takes place. And so it would be hard to separate out observer acceleration from that change, I think. So we might not be able to do that other than the obvious stuff due to the motion of the Earth around the sun. But we wouldn't be able to do anything about acceleration between two objects in the galaxy or between two objects in other galaxies, I think.
All right, great.
That's right. Not thought about that one before. It's a good question.
Okay, all right. So there was a query by, if I get the name right, Kiwi Liang. And the query is, would you please comment on the pulsar timing array and the possibility that it could be used for distinguishing general relativity from some modified theory of gravity?
Right. Well, there's been quite a bit of work going on using pulsars to check out theories of gravity. The binary pulsar that I talked about briefly is probably the best one, and it is already putting significant limits on some of the other theories of gravity. Einstein's theory is standing up okay. The others are beginning to be eliminated or are only true in very limited and often extreme circumstances. So, yep, pulsar timing will undoubtedly give us more information on this with time.
Okay. So there's a question by Navunil Saha, and the question is there any possibility of detecting the mergers with future space-based detectors like LISA or DESIGO, is it? Especially in the low frequency domain.
Right, yes, LISA is, I think, a European project, space-based project to detect gravitational waves using several satellites, and the distance between the satellites changes as a gravitational wave goes by. And that is certainly the European one is on the books to fly. It's still being built. So, you know, it's yet to launch successfully, and it needs the successful launch of several satellites. But it should work well, and it will give us information at higher frequencies, not as high frequency as the pulsar people, but at higher frequencies than the ground-based detectors. And so we will be gradually filling out the spectrum of gravitational waves. At the moment, we're only working, so to speak, just at the right-hand end of the spectrum. So LISA will push a bit more to the left, the pulsar timing array even more to the left. So it's coming, but it hasn't actually happened yet, either LISA or much on the pulsar timing arrays doing some of it.
Okay, I think we'll end with the last query, again from Arnav Das, which is, if gravitational wave detectors rely on interferometers, will the expansion and contraction of space not strain the light waves within the detector as well, thereby making the strain undetectable?
I think the answer must be no, because they have detected it, but I do see the question he's asking. I'm not quite sure what the answer is, to be honest.
Okay.
There must be an answer because they can detect them.
All right, great. So I think with that, we come to the end of this beautiful session. And let us thank Professor Burnell, not only for her lecture, but also for her patience with so many queries. So thank you so much. And we are so happy, so glad, so grateful that you could find some time out and speak to a very diverse audience. And so I think with that, we would conclude the session in this series. And I'd like to thank the incredible team of the Physics and Astronomy Club and the Roorkee Chapter of the Indian Physics Association, and of course, the Institute Lecture Series Committee for their support. So with that, thank you so much, Professor Burnell. Please stay safe.
Thank you very much. Stay safe, everybody. Keep well. Thank you for your interest. Thank you.
Thank you. Bye-bye.
Bye-bye.
All right, team. So with that, we are ending the meeting. Thanks once again. All of us have a great day. Please do fill in the feedback. I'm assuming it has been posted by our diligent team. There it is. Yes. Please do fill in the feedback. And so we meet this Saturday once again. So please tune in then. Thank you so much. Bye-bye.
Thank you.